In this lecture, we are going to discuss about test signals. So whenever we are having a system, an actual system or a mathematical model of the system, we always want to make sure that whenever that system is put under actual condition, it should behave satisfactorily. So before putting any system in actual condition, we always test it under predefined condition. So mainly performance of the system depends upon the type of input that it will be having. There are various standard signals we are having. So when a system performs satisfactorily based on these standard type of input, so it is expected that it will going to perform satisfactorily under actual condition. So let's see what we are going to cover. We are going to cover a step input, a ramp input, parabolic input, and then we will discuss at the end impulse input in this lecture. The first signal is step signal. The step signal is whose value changes from one level to another level, that is mostly from 0 to some value in 0 time, or we can say in a fraction of time or fraction of second, then that is called as a step signal. So graphically this is how step signal will look alike. So at 0 it will be having 0 value, and at next instant it will be having some value, say a here, and that value will remain until we switch off the signal. So we can write this signal as r of t, and that will be equal to a into u of t. So this is how the step signal is represented in time domain. It will be a into u of t, where u of t will be equal to 1 when we are having time t greater than 0, and it will be u of t will be 0 when we are having time less than equal to 0. So this function will be having 0 value when time is less than or equal to 0, and when time is greater than 0 it will be having value 1. And here a represent the magnification, and this a value will define what will be the magnitude of this step signal. Now let's convert this time domain function into frequency domain by applying Laplace transform. So by applying a Laplace transform, we can have Laplace of r of t, and that will be equal to Laplace of this term a into u of t. So a is a constant, we can take it out and we will be having Laplace of u of t. Now as u of t is 1 when time is greater than 0, so if we substitute that value here, so it is a into Laplace of 1, and we know that Laplace of any constant, that is 1, it will be equal to 1 by s. So we can write it here, so a by s. So here this a by s value represent the step signal, and that we will be writing as r of s. So this is the step signal value. Now this step signal is also called as a position function, because the graph of this step signal is same like when we talk about the position that is constant with respect to time. So if we plot the graph of position which is constant with respect to time, will look like the step signal graph. So in that way it is also called as a position function. Next we are having a ramp signal. So ramp signal will start from value 0 and it continuously increases linearly with respect to time. This is how it will be represented on graph. So on x-axis we are having time, on y-axis we are having the response of the function, and we can see here at time t0 it is a 0, and then after that it gradually increases with time. So this is how ramp input is represented. Now mathematically we can write ramp input as r of t is equal to a into t. So this will be the value when time t is greater than 0, and for time t less than or equal to 0 we will be having a 0 value for this function. So again we can write this function or this ramp signal in a frequency domain by taking Laplace. So again if we take Laplace transform, so it will be written as L of r of t, that is equal to, so again a is constant, we can take it out, and Laplace of t, that is a variable. So we know that when we take Laplace transform of t, so it will be 1 by s square, because here we are using formula t raised to n. and when we take Laplace of t raised to n, it will be n factorial upon s raised to n plus 1. This is the formula in Laplace transform. So here what is happening, power is 1 for t, and when we take the Laplace, so it will be 1 factorial upon s raised to 1 plus 1, that is 2. So here we are having 1 upon s square. When we take Laplace on left hand side, it will become r of s, and on right hand side it will be a by s square. So this is the function value of the ramp signal, and this ramp signal is also called as a velocity function. So again, when we are discussing about any system where we are interested in a position, like we are having a shaft which is rotating, we are interested in the angular position of that shaft. So when we determine how position is changes when velocity of that shaft increases linearly, so that position when we plot on graph paper will going to follow this nature of a ramp signal. So that's why it is called as a velocity function. Next signal we are having is parabolic signal. The parabolic signal will begin at 0 and increases parabolically in this way. So again at 0 we can say that it is approximately 0, and then as time increases it gradually increases in this way in a parabolic fashion. So again, in mathematically we can represent this form in time domain as r of t is equal to a into t square by 2. So this is the function value when time is greater than 0, and when we are having time less than is equal to 0, so in that case we can consider that it is having value 0. So again, to know what will be the value or function value in frequency domain, we can take Laplace transform of this expression. So again, by taking a Laplace transform, we will be having Laplace of r of t, and that will be equal to, again here a is constant, so we can take it out, and we will be having Laplace transform of t square by 2. So again, we will be using here the formula of Laplace transform of t raised to n is equal to n factorial upon s raised to n plus 1. So if we apply that formula, we will be having a into, this will be 2 factorial, so that is 2 divided by s raised to 2 plus 1, that is 3, and into we will be having this 2 here. So this 2 and 2 will get cancelled, and we will be having a by s cube. So this is the parabolic function value in frequency domain. So now here, if we are having a value as 1, so if we say that let a is 1, so here this value or this r of s will become 1 by s cube. So this we can say as unit parabolic signal. Similarly, for step input and ramp input, if we take a value as 1, then they will be called as unit step input and unit ramp input respectively. So this parabolic signal is also called as a acceleration function. It is because of the nature of curve that we are having here, or nature of the signal that we are having here. So it is again, if we are considering any positional system where we are interested in position of the object, position of that object changes because of the acceleration in the system. When we plot the position considering the acceleration in the system, so that position will going to follow this nature. So because of that, this parabolic signal is also called as a acceleration function. Next type of signal is impulse signal. So when we talk about the impulse signal, it will be having a zero value at every instant except when time is equal to 0, or we can say in fraction of second we will be having a very large magnitude, and that magnitude will go to infinity. So that kind of signal is impulse signal. So this is how we can represent it. So in a fraction of second it will be having a very large value, and then after that and before that it will be always having value 0. Impulse signal are also called as a delta function, and they are represented as delta of t is equal to a for time t is equal to 0, and it is 0 for when we are having time not equal to 0. So at any instant we can have a very large value, and then before and after that instant we will be having zero value. So that kind of function is impulse function. Now again, to convert this into a frequency domain, we can apply a Laplace transform, and when we apply Laplace transform, we will be having a Laplace of this delta t, and that will be equal to a for this case. As here the magnitude of this impulse function is a, so when we take Laplace transform of delta function, it will be equal to 1. So we will be having Laplace transform of delta t will be equal to a. So all these signal we can use based on the type of input that we may require in order to analyze a given system. So if we are having input which will be like a shock, so in that case we can use impulse signal. If we are having input which is changing from one value to another value suddenly, so we can use step input. If we are having an input which is gradually increasing with respect to time, so for that we can use ramp input. And if we are having an input which is increasing parabolically, so for that case we can use parabolic signal. So in this way, based on the type of input that we desire in order to analyze a given system, we can use all these test signal. So here we'll end this lecture.